We will often be confronted with data that is coming from a population that either we don't know a whole lot about, or that we do know something about, but we know the population is not actually normally distributed. In these cases, we might still be interested in the mean of this population. It's just a mean that's coming from a non-normal distribution. And so we might want to be able to form confidence intervals for this mean, even though we're not going to assume much about the population distribution. And when we're faced with this situation, the main tool that's going to be at our disposal is the central limit theorem. And so by invoking the central limit theorem, we can still say something about the sampling distribution of the sample mean. And using this sampling distribution, we can in turn construct confidence intervals for the mean as we require. So if the population is not normally distributed, but if we're willing to assume that we still know the variance and that the sample size is large enough to invoke the central limit theorem, then we can do that and actually say something about the sampling distribution of the sample mean, or at least about the approximate sampling distribution. So in the setup, we have x1 through xn coming from some unknown population, or maybe we know something about it, but we know that it's non-normal. We're also going to assume that the mean is mu and the variance is sigma squared, but that we don't know what the mean is, right? We want to end up forming a confidence interval for the mean, and so we don't know the value of the mean. Instead, we'll just assume that the variance is known, right? It's a non-normal distribution, but we still know what the variance in the population is. Now, this might not be a super realistic assumption in all settings. However, if we do know what the variance is, then we can proceed directly from the central limit theorem here. In order to use the central limit theorem, we need to assume that n is large enough to invoke it. And so again, this might mean that we take n to be greater than or equal to 30 if we have some sense that the population is approximately normally distributed. If we really don't know anything about the population at all, we might want a slightly larger n, maybe around 100, to invoke this. But either way, we're going to assume that we have a large enough sample so that the central limit theorem actually applies. Then based on the central limit theorem, the sampling distribution of the sample mean is going to be approximately normal. And so specifically, we're going to be able to say that x bar follows an approximately normal distribution with a mean of mu and a variance of sigma squared divided by n. This is just an invocation of the central limit theorem directly. We can take our standardization trick from the normal distribution. And so if x bar follows a normal distribution with a mean of mu and a variance of sigma squared over n, then if we take x bar and we subtract off its mean and we divide by the standard deviation, this always leads to a normal 0, 1 random variable, right? And so ultimately, we can say that the standardized version is going to follow the normal 0, 1. And then we can use this form of the standardized version to form what we would call approximate confidence intervals for mu. Now, these intervals are approximate because the sampling distribution is not exact. It's an approximation based on the central limit theorem, and with a large enough n, it is going to be a good enough approximation to make use of. However, it's important to know that this is not an exact confidence interval. Importantly, as soon as we're at the point where we're making the statement that x bar minus mu over sigma over the square root of n follows a normal 0, 1, this is exactly the same setup that we have when we're trying to do a normal-based confidence interval. That is to say, if we had actually assumed that x1 through xn came from a normal distribution themselves, right, where they come from their normal mu sigma squared distribution, then this is actually no different, right? Because if we had assumed this, then we wouldn't need to use the central limit theorem, right? But we would get that x bar follows the same distribution. And so our confidence interval actually doesn't need to change, right? So this is exactly the same setup that we would have as if we had assumed normality from the start. So if we take z alpha over 2 to be the critical value from the standard normal at the alpha over 2 level, right? So this is the value that if you were to plug into the CDF of the normal, you would get alpha over 2 out of it. Right? Then we can form a two-sided confidence interval by taking x bar plus or minus z alpha over 2 times the population standard deviation divided by the square root of n. This is exactly the same form that we have for the normal distribution. And the reason it's exactly the same form is because as long as we can use the central limit theorem, the sampling distribution is exactly the same. The sampling distribution of the sample mean is exactly the same thing as the approximate sampling distribution of the sample mean, whether we assume normality or not. It's just in the case of not assuming normality, this is an approximate result. It's not an exact result. right? So it takes the exact same form as what we would see if we had had a normal population to begin. And so what this is suggesting to us is that the assumption of normality is actually not that important of an assumption. We can use the exact same confidence interval even if normality is not properly assumed, again, as long as our sample size is large enough. It's important to keep in mind that this is not going to be an exact confidence interval, and so it might be the case that if you were to actually do this, you don't find properly a 95% coverage from your 95% confidence intervals, right? You might be a little bit off on this, but the differences, as long as it's appropriate to apply the central limit theorem, are going to be fairly small, and so they won't make a big difference to that. The other piece to note is that as n increases, right, we expect any given interval to get smaller, but the other thing is as n increases, the central limit theorem becomes more and more accurate. And so for larger and larger n, this is going to become a better and better approximation to the truth, right? And so we will expect that the performance of the intervals actually gets better as we increase our sample size. We can take a look at an example of how this might be applied. And so in this example, we have that a biologist is studying the wingspan of some butterfly species, and it's known that the population standard deviations is 0.5 centimeters. We take a random sample of 400 butterflies and find that the average wingspan is 3.2 centimeters. And using this information, they want to give a 99% confidence interval for the average wingspan of these butterflies, right? And so if we go through and read what we have been given here, right, it's important to note that we have the population standard deviation, right? So that's going to be 0.5 centimeters. And so we know that piece of information. We're taking a random sample of n equals 400 individuals. Now, as soon as you see that n equals 400, this should be suggesting that we can definitely apply the central limit theorem, right? This is a very large n, much larger than 30, much larger than 100, and so the central limit theorem is going to apply, and so that's going to be great news for us. The other piece is that we find the sample mean is 3.2 centimeters. We want a 99% confidence interval, and so then we can end up forming this, right? And if we think about just the general format, right, our general format is going to be x bar plus or minus z alpha over 2 times by sigma divided by the square root of n, right? X bar we know is going to be 3.2. Z alpha over 2, right? Well, we want alpha, and alpha is always 1 minus our confidence level, right? So that's 1 minus 0.99. So alpha is going to be 0.01, which means that alpha over 2 is 0.005, right? So we're going to want the critical value from 0.005. Sigma, we are told, is 0.5. And then n is 400, right? And so because we can use the confidence intervals based on this normal style interval here, this is going to be all we need to do. We just plug in our values here and solve for what that interval actually has to be. And so if we do that, then we can see that because it's large, we can use this format, right? X bar is 3.2, sigma is 0.5, n is 400. Alpha is 1 minus 0.9, so 0.01. So we want z alpha over 2. This corresponds to a critical value of negative 2.58. If you were using statistical software, we can find this using the Q-norm function in R, right? And we take Q-norm, and then you have to plug in whatever you want here. So alpha over 2, which is 0.005, right? So that's going to give us our 0.005 there. Okay, so we get our critical value is 2.58. So the ultimate overarching confidence interval is going to be x bar plus or minus 2.58 times sigma over root n, which is 3.2 plus or minus 2.58 times 0.5 over the square root of 400. And if you work out the endpoints there, you should get 3.14 approximately up to 3.26 approximately. And so then the mechanics of calculating the interval end up becoming plugging into this not overly complex formula here. So the important piece is all of the work we had to do to get to this point, right? We had to be able to make use of the approximation based on the central limit theorem. We had to know that we could use the normal sampling distribution here. And so there's a lot that goes into these confidence intervals, but once you're able to identify this is the type of confidence interval we need, and you can start to pick out what is the information that's given to us in order to actually work through this confidence interval, the mechanics of calculating the confidence interval become a matter of plugging in, adding, and multiplying some numbers together. So the large sample confidence intervals, they're quite useful because we don't need to assume anything about the population distribution. However, they have one major drawback, and it's the same major drawback that the normal-based confidence intervals have, which is that they assume that the variance is known. If we do not know the population variance, these intervals are not going to work, and instead we're going to have to turn to other techniques in order to find confidence intervals for unknown variance situations.